Okay. All right. Let me share my screen. Okay. So everyone, super sorry about the technical difficulties. It's like the first time this happened, so probably gonna figure it out. Thing with Zoom later on. But yeah, welcome to Multimodal Weekly. This is a weekly webinar series hosted by the team at 12 Labs. We've been doing this, every Friday over the past year or so. Some of the topics that we can cover on a weekly basis, including new research in multimodal and high prediction models, application in multimodal and different verticals, new video and multimodal projects that people like to share, and sometimes team members from 12 Labs talk about the tutorials and guides on using our platform. I've been inviting a lot of researchers in our session in the past couple of weeks, ranging from working on multimodal LLMs to video understanding to multimodal intelligence, video and question answering, etc. So yeah, this is definitely an exciting domain of research that I would love to get our community to become more aware. So for today's session, we have three researchers talking about a variety of different topics. Xiang Yue is going to be the first speaker. He will give a talk about his latest work, MMMU, which is a massive multidisciplinary multimodal understanding and reasoning benchmark. Then we have Orr Zohar from Stanford. He will share about his project VideoStar that's specifically focused on video instruction tuning. And then we'll close out the session with Mingqi, currently a student at Oregon State, talking about explanation method for different vision backbones, namely convolutional neural networks and transformer. Yeah, so with that, quick note on the logistic. Attendees, feel free to send your question on Zoom chat, and then after each speaker finish, we can have a short Q&A session. Where you can ask them in real time. So I stop sharing my screen, and yeah, I unmute Xiang, and now you can go ahead and share your screen and start your presentation.
Sure. Seems that I cannot share the screen.
Can you try again? All right, awesome. Let's get ready.
Cool. Hi everyone. It's very exciting to meet everyone here. And my name is Xiang Yue, and I'm a postdoctoral researcher at CMU right now. And today I'm very excited to talk about our recent benchmark, MMMU, a massive multidisciplinary multimodal understanding reasoning benchmark for expert AGI. So basically, if you track the progress of the recent ML development, you will find that the most recent notable ML models are all multimodal ones. And this is a figure taken from the AI Index report this year from Stanford. And you will find that, we have like Gemini, GPT-4, as well as Cloud 3, etc. And all of these foundation models are all multimodal ones. I think one of the reasons is because, we really expect our models can see this world, not just, speaks. So we expect our model behave like humans, and we expect our models can empower the real applications. And on another perspective, we expect our model to become more and more intelligent and to achieve so-called experts, to achieve so-called like artificial general intelligence. However, everyone has their own definition for the artificial general intelligence, or AGI. It's really hard to define what does AGI mean. And in this paper, we just basically follow the Maurice et al., which published the paper in SML this year, basically just classify the AGI into 5 levels, from level 1 to level 5. And among these levels, we think the level 3 expert level is quite important, because basically the expert level AGI mean the model is expected to outperform at least 90% of the skilled adults. And this is a substitution threshold for machine intelligence endure human labor. And therefore, it's both intellectual and societal importance to closely monitor the progress towards expert AGI. Well, However, measuring the expert AGI is not a very easy thing. On the one hand, we expect the model to have a very broad coverage of the knowledge. And on the other hand, we also expect our model can do in-depth reasoning. While existing multimodal benchmarks are, either they are like just cover very basic, simple facts or ask very simple questions, or they just coverage like their breadth just cover very limited topics. So and in this work we basically wanted to propose a benchmark that can measure the expert AGI, and we propose using the college level exams for this, because the college level exam is were just developed to evaluate the human intelligence. So it's very natural to think about like we can just use how we evaluate human experts to evaluate the model. The MMU benchmark is such a kind of benchmark. And it basically means we have collected exam questions from like multi-disciplines covering multimodal understanding and reasoning. And from the breadth perspective, we basically collect like 11,000 college level problems across 6 broad disciplines and 30 college subjects. And we also have like 30 heterogeneous image tags. And from the depth perspective, we basically have interleave text and multiple images sometimes, and we also have like expert level perception and reasoning, which require deep subject knowledge. And here are more examples of MMU questions, and for each question we have like different kinds of meta information, which includes discipline and their question type, whether it's being multiple choice or open. We also have the subject, subfield, image tab, and difficulty, those kind of meta information associated with each question. And MMU became very popular in the community since it's released, and like many industrial model developers adopted that's one of the key metric to monitor the progress of the multimodal models. And so far it has been downloaded. So this kind of some older status, but right now it's like more than 1 million downloads on Hugging Face. And it's also covered by a lot of AI blogs posts, especially for this year Stanford AI Index report. It just like deemed the MMU as kind of important benchmark or metric to monitor the reasoning capability of foundation models. And then we want to ask why MMU, why people want to use this benchmark. So firstly, we think it's because the MMU had a very rigorous data curation process, which leads to high quality data. Basically, we actually have a very rigorous data collection pipeline. And as the first step, we try to sort of the different kinds of subjects. The way we did that is basically we just refer the university majors. And then we just remove the majors which do not have the visual inputs. Because this benchmark was mostly developed for multimodal reasoning instead of text only. For example, for some law questions, they just basically they're pure text, and they do not have any images or video inputs. So we just remove those kind of university majors. And finally, we have like 30 subjects or majors lying, the 6 disciplines. And then for each major or for each subject, we just let the human experts, all the college students, annotators to collect questions from their textbooks, some other online resources. And finally, we had like around 13,000 questions in total. And at the final step, we did a very rigorous quality control. And we basically just remove some duplicated questions. And we also check, if some questions are are either, they're very simple, just remove it, or some question, they're not, not suitable for this benchmark, just remove it. And we also did a lot of format and typo checks to unify the format. And finally, we also categorize the difficulties like based on the human experts expertise. And here are more statistics of this benchmark, and we basically have a relatively even distribution of the difficulties. And we also have like different kinds of image tabs covering like different kinds of subjects. And the second reason is that, we think the MMU benchmark is very effective suit for tracking the multimodal model development. Like from this figure, we can just see the progress of the multimodal development. And as we can see, in the past few months, both open source and closed source models have made significant progress. Like the gap between open source and proprietary models were closing, but has recently widened again after the release of GPT-4. But luckily, I mean, in the last month, we also see an upgraded version of InterVL 2.0, and that was also an open source model. And the gap was closing again, and basically the model achieved like more than 55% accuracy. So basically, like we also see like another update from the open source community. So this is really great. But even that, like even the best property model like GPT-4 still has significant gaps compared to human experts. So we think maybe there's still or there's still a long way to go especially if our goal is to achieve kind of expert level AGI. And finally, we think the MMU is an excellent model diagnosis tool. Because we have like different subjects, you can basically just check out the accuracy of like different subjects. For example, here we can see the like for the art design, here's medicine, humanity, and social science. Basically, these three disciplines models accuracies are relatively higher than the others, and the gap between the best models and the human experts is not that large. However, if you check out the business, science, technology, and engineering, you find that the model usually struggle with these subjects. Because for this kind of disciplines, they usually involve more complex reasoning questions. And you can definitely also check out the difficulty specific accuracy. Basically, you can just check out whether your model can answer easy questions or whether there's still struggle to answer easy questions. And we can see, like from this figure, we can see the GPT-4 vision actually outperforms open source models in the easy and medium question, but not hard. For the hard question, I think like all of the models struggle with hard questions. But the closed source model might did a better job in answering like easy and medium questions. And you can also definitely check out the image specific accuracy because we have like 30 image tabs. And there are some many interesting like conclusions. For example, GPT-4V is better at comprehending tables, plots, and domain-specific images compared with open source models. And you can also check out the single image versus multiple image accuracy because we definitely have multiple image question as well as single image question. And most of the models generally struggle with reasoning over multiple images. But Vela, one of the open source models by NVIDIA, like did a relatively good job in multiple image reasoning. And we can also like do some error analysis to find out or to see like in what kind of situations our model can do a good job, well, what kind of question they are not good at. And from the error analysis based on the predictions by GPT-4V, we basically see the errors most lie in the perception, lack of knowledge, and reasoning. But firstly, I want to strengthen like I think the one of the like very important thing for the modern foundation model is basically like they just use language as a vehicle. This is very important because model can just use language as to explain what it sees and the rationale for the prediction compared with the previous multimodal models. But still the knowledge, I think the knowledge is the foundation for both perception and reasoning. And we often found errors it's because like the model just lack of deep subject knowledge and which could lead to perception and reasoning errors. And grounding and referring is kind of challenging as well because the model seems that the model is not very good at grounding and also some spatial reasoning thing. I think this phenomenon is kind of also covered by some other work as well. And finally, for the complex reasoning, I mean, GPT-4V demonstrates moments of accents in complex reasoning, but they still tend to like generate some hallucinations, if the reasoning chains are very complex. And yeah, this is all for the MMU, and we recently like got another upgraded version, which we may call the MMMU-Pro. Basically, we just wanted to solve some existing issue of MMU. So for example, people say, okay, your benchmark is great, but in many cases, the model's performance is strongly correlated with the language model, but the perception set is relatively weak. So we just wanted to kind of augment this vision part. And the second limitation of the MMU is like usually it's a multiple choice question, and then the question just have 4 options. So in some cases, model can just do the shortcuts, can just guess the answer because the random guess accuracy is just like 25% accuracy. So we just wanted to avoid such kind of random guess behavior, and basically we just augment the previous options from the 4 to 10. And we also kind of augment the setting where basically we just take a screenshot of photo of the the question with augmented options. And definitely we also got some simulated backgrounds. And then we just take kind of the screenshot and just feed this kind of screenshot or the photo to the model and just allow the model to answer instead of inputting like the both question, text question, and image. And another setting we augment is basically we augment the multi-question in a single image setting. Basically, this is just one image or one screenshot, but it has like 4 or 3 questions. And we just allow the model to answer this question in one time. And we also found like the accuracy drops a lot when they just did those kind of compositional reasoning, or just you expect the model to generate the answers for all the 3 or 4 questions in one shot. Yeah, and we'll basically release this kind of pro data set maybe in the next couple of weeks. And hopefully it can address some existing issues of MMU, and it could let the and kind of reflect the model's visions modules like its importance compared with the current text part. And to conclude, we think the MMU is a good benchmark to monitor the multi-models development. But we should also caution that the MMU is not a sufficient text for expert AGI. However, we believe that it should be necessary for an expert AGI to achieve strong performance on MMU. And future efforts should aim at closing the gap between multimodal models and human experts if our goal is want to achieve expert AGI. And finally, we just want to thank all of the like authors from like 6 different institutes, as well as the student volunteers for helping annotate the questions. And we are also grateful for the model developers and the community. And we really appreciate their feedback, their report issues to make the benchmark better. Yeah, thanks again for the invitation, and yeah, super happy to answer any questions.
Yeah, thanks, John. Since we running a little bit low on time, I think we can do the Q&A actually target in the Zoom chat. So there's one question by Rina. So if you can answer that one on Zoom, that'd be great. So let me.
Sure.
Absolutely. So I want to unmute R, and yeah, go ahead and start your slide.
All right. Hello, everyone. Moment. Hello, everyone. So my name is Orr Zohar. I'm going to present to you my recent work, Video Star, where I essentially investigate how self-training can be used to essentially weaken the strict requirements for instruction tuning datasets for video models. I'd like to start by thanking my co-authors, Xiaohan, Jonathan, Dan, and Serena. Yeah. So I kind of wanted to start about why we even care about video LLMs. And in my mind, there's just like a lot more possible applications that these models have. They're very diverse. They can be applied to anything from being AI coaches for AR, VR settings, all the way to being used in surgical assistance and AI-assisted surgery. And the other part that's very important, of course, for video instruction tuning is what is video instruction tuning. So the way these models work is they essentially, you give them examples of video question or prompt and output text triplets, and you essentially train on these types of data sets. There's an additional pre-training stage that typically isn't really done right now, at least not in the open source community. However, collecting these data sets is very difficult, because if you wanted, for example, to do it via humans, you now need the human annotators to watch long videos, ideally, meaning 20 minutes to 1 hour videos, and start coming up with like question answer pairs. And these data sets tend to be, therefore, relatively ambiguous. And of course, each new task that you want to, or new application that you want to get to, will require you to re-annotate now these types of data. So it's essentially hard and expensive, right? In terms of existing approaches, of course, the bottom, that's what we just talked about, how a human would annotate it. An alternative approach would be more of an automated approach. And currently what people do is they'll caption videos and then they'll prompt stronger language models like ChatGPT to generate question answer pairs. And that's essentially how they will derive these instruction tuning data sets. And however, I found when I was looking at the instruction tuning data sets that this has a lot of drawbacks. They're kind of like building on the quality of the captioned text to be able to come up with QA pairs. And if you look at existing data sets, you can see here in blue that the majority of them tend to be essentially prompting for video captions. You can see in terms of percentages, like the top question, what is happening in this video? It constitutes about 5% of the data set, and the rest of the most common questions aren't a lot. They also essentially prompt for video captions. When we look for more grounding style questions, here in the bottom, you can see that their percentages are basically negligible. So this, of course, leads to issues when you try and now train on these data sets for SFT. And the way I approach the project for Video Star is I basically try to think about the problem as essentially have some sort of trade-off between, for a particular data set size. Let's say you have 100,000 annotated videos. You're going to have, and let's say you have many more unannotated videos. And then you're going to have some trade-off between the data that basically for that particular data set, how much compute you would like to spend also for generation, for example, right? So as opposed to training, right? So you can either spend your compute just training vanilla for multiple epochs in the same data set, or you can alternatively, for example, perform generation cycles as part of your training and then augment that and hopefully improve your performance. So that's kind of how I view it. Of course, if you flip the axes and you just have more and more compute, then the graph will of course just go up. But I think that's less realistic. And the question is like, for some like compute budget, how can you get the best performance? And now to VideoStar. So basically, the idea being here is basically the VideoStar can be applied either to improve general LMM video QA performance, or it can be used to adapt models to new tasks. And basically, the outline is that you start with some labeled video data set. These can be labels of any type: classification labels, different types of metadata that you have about what's happening in the video, bounding boxes, temporal action localization. And VideoStar essentially iterate between generation cycles, filtering these same generations, and SFT. And I just cycle between these approaches. And of course, at the output, you're going to have your instruction tuning data set that can also be used to train new models, but also and then you also get a better model, right? And then the SFTs, you perform it on that model, and then is hopefully better. If we look at it in a bit more fine-grained manner, I go essentially through answer generation, and then I verify whether the label exists or not in the generated answer. If this generation is unsuccessful, meaning that the labels do not appear in the answer, then I do label rationalization. That's the second box on the right, the third box on the right. And again, I try to verify the existence of the labels, the ground truth gold labels in the generated answers. Both of these produce an SFT data set, which I train, and then I repeat this cycle. And that's kind of like an overview of the overall methodology. Now let's look at what each one of these bounding boxes are in answer generation. You're essentially prompting the model to directly answer the question. There's nothing special about this. You give it the video, you give it the question, and it answers. In label rationalization, you give the model both the question and the labels, and you ask it to rationalize these labels, right? So if it's for example, here in kinetics, sorry, this is and soon we'll get into which benchmarks we use, but this is on star benchmarks. You give it in this case, the answer to the question, but we also have examples for, let's say, the bounding boxes or whatever label you're using as supervision for that generation. And the model has to back rationalize that label. In terms of the verification, we essentially introduce like this parser verifier pair, where the parser is primarily tasked with essentially, you have free-form text, but you actually need to compare the predicted labels, right, that are contained inside that text. It's going to be, like I said before, bounding boxes, like temporal timestamps, whatever. So the parser essentially does this action through entity recognition or regex or NER, etc. And the verifier just compares the gold and predicted labels using like appropriate comparison matrix. For each one, of course, you would have a different comparison matrix and metric. And I wanted just to kind of like look at a typical data flow, like how a particular example will flow through this chart, right? That I just introduced. So for this particular example, you essentially start answer generation and it fails. That's the first red X in the chart, and you get to label rationalization. However, in label rationalization, it again failed to accurately predict the overall score. This is specifically for action. This is for a data set called fine diving, where you want to predict the overall like diving score of a particular Olympic dive. So and then your final supervision will be the overall score, as well as, let's say, some additional labels that data set contains. So this unfortunately failed again. However, of course, other samples succeeded. So essentially, you complete the cycle with the correctly answered examples, right? But this particular example failed. In the second cycle, again, you start with answer generation. It failed again. However, this time when you go to label rationalization, the model is able to this time accurately predict the score, or at least rationalize the score such that at least it appears in that generated text. So now it is included in the training data set, and the cycle is completed. In the final, this is like the third. This is essentially the third cycle, or cycle number 2. This time, it essentially correctly answers the question already in answer generation. So So this is kind of like maybe gives you the idea of how an answer that's initially answered incorrectly, and then the model is able to essentially directly answer the question after a few training cycles. Yeah, and basically these are graphs. For our study, we used 3 data sets, the kinetics data sets, and it's essentially an action classification data set. The STAR benchmark, which has both bounding boxes, temporal action localization, and situated reasoning. So it's more like also has actual like QA pairs. And the fine diving data set, this is an action quality assessment data set. So these are Olympic dives, and you have like an overall score for each dive. And you can see here in the graph, of course, for example, kinetics is a relatively like, easy benchmark. So of course, you had actually even high rates of direct answer generation already in like essentially with no STAR cycles. And of course, that increases to close to 100% as we progress, as opposed to the STAR benchmark, where initially like answer generation was at around 2%, and that rose to over around 30% by the end of the second cycle. And in fine diving, you had almost no, you had actually completely no direct answer generation in the first cycle, but very little label rationalization in the first cycle. And that improved over time to, in the end, I see we had like over 25% direct answer generation and close to 60% label rationalization. And of course, the STAR cycles can be completed until you convert most, or essentially until these graphs essentially will saturate. Some of them probably won't saturate 100%, but in fact, eventually they will saturate. So I just wanted to show, again, these are the 3 benchmarks, the 3 source data sets. If you want to see more examples, I have a QR code for like a Hugging Face demo. And you can see our examples. I really like the kinetics one, where essentially, if originally like the only label you had for the video, you had this video and the label smashing, now you have essentially this QA pair of like what activity is being performed in the video. And the answer is like in the video, a man is seen holding a large axe, which is true. And they also identified the crowd, the fact that there's a crowd in the background. It then hits a block of wood, and it essentially is even more fine-grained, where it even identifies the fact that you're like chopping wood, right? So I kind of like that it can kind of show you how it can even produce sometimes grounded examples. Of course, label rationalization particularly can also hallucinate, which is why actually we don't include it in our final, like in the final training cycle. We actually only use directly generated answers exactly because of hallucination. In terms of performance, we saw a nice improvement here. Maybe I'll just also explain what our baselines are. In video-LLM Plus, that is essentially video-LLM, but where we essentially train on exactly the same data sets, but without STAR cycle. So we just train on the vanilla, like essentially the LLM generated questions, and the output value is just literally like that label, right? We did sometimes template it a bit, but very not very robustly, just like the answer is or something along these lines usually. And the idea was to compare, like, okay, like of course we're adding more data, but can we if we just do a simpler approach, how would that fare, for example? And you can see that we had a nice delta in terms of performance over video star in our different baselines. In terms of adapted data sets, again, like I said before, we both have the like overall performance. We also want to adapt LMMs to new data sets, to new tasks and applications, right? So this is essentially mimicking the fact, for example, if you want a judge for some Olympic diving event, right, then you would have these like overall scores, and you want them all to become better at predicting these scores, for example, right? Or if or this could be also for kinetics or any task, right? The idea is and here we saw essentially on the adopted data sets performance improvements of between 15 to 33%. I personally theorize that this has to do with like the number of STAR cycles that we did. I think that if we would have continued to do this, then essentially we would just have converted a larger portion of the data sets, and that would have reflected in performance. The percentages are also, I'll say, they're also very close to, relative to also like the amount of final videos that are actually converted in that data set, right? So fine diving is both a small data set and it had a relatively small conversion rate, and then we saw like the smallest improvement. But yeah, that's kind of like the idea. And just to maybe motivate this, like, could we use LVLMs or LMMs as, for example, like Olympic judges or different or you know, an AI-assisted surgery and all these like very, I think, exciting tasks. I think that's I think it's possible. And maybe VideoStar will be one way to broach this. And yeah, that's it for me. Thank you all for listening. You have here a QR code to our project page. Again, I'd like to thank my co-authors and Google, of course, for funding this project. Yeah, this project was joint between Google, Stanford High, and Google AI Research.
Awesome. Thanks all. I really appreciate you walking through the details of the project. And yeah, I think it's a very valuable contribution to video understanding field with like, you know, the label data set, right? And definitely significantly reduce the hurdle it takes to collect high quality data, you know, to train this powerful video understanding model. So excited to see, you know, future work from your team to extend this work to improve the state of the field.
Yeah, I definitely think that, especially if you can think towards maybe industry companies that can actually even go broach pre-training, I think such things even become more attractive because you're more playing about like data set even sizes, right? So you can think, so maybe even there the quality would even matter even a little bit less than they would in SFT. But you could essentially expand your data sets to many data sets. Almost all videos have some sort of auxiliary label attached to them, some sort of metadata. This could be location, this could be like the person who's taking the photo or some small caption. So I think being able to leverage all this like supervision that's not good for SFT, but you could essentially blow it out to essentially very large like interleaved video text data sets or even conversations. So I think, yeah, I'm very excited about this direction. And if anyone wants to talk to me, feel free to reach out. My email is on my personal website. It's, yeah, you can see it here as well. It's part of the project link.
Awesome.
Thank you all.
Yep. Yeah, and if you have any question for about this project, feel free to put in the chat. So I'm gonna unmute Mingqi, and yeah, let's go ahead with the final speaker.
Okay. Yeah. And, okay. Okay. Hello everyone, and my name is Mingqi Jiang, the first year Ph.D. student of Dr. Li Fuxing from Oregon State University, and thanks for the invitation. And I'm very happy to be here to talk about our latest work on deep model explainability. So, ever since the beginning of deep learning, explaining the decision-making mechanism of deep networks has been an important topic. A popular approach is attribution maps, which shows presumably important regions for classifiers to make their classification. There are several different types of attribution map algorithms, including gradient-based, perturbation-based, and optimization-based. Our group has contributed optimization-based algorithms, EGOS and EGOS++. A central idea in the evaluation of these attribution map algorithms is to send occluded images as input images to the deep networks and examine how the network would perform on those occluded images. For example, in the middle image, we occluded the parts the attribution map deemed the most important, which is the head of the bird and the tail of another one. And suddenly, in this case, the CNN network no longer recognizes it as a black growth class. However, this is not merely adversarial. On the right-hand side, we show that if we only reveal this one head and one tail, the CNN already classifies with very high confidence. This felt a bit crazy to us that for CNNs, it was really fixating on the head and tail and ignoring all the other parts of the bird. This raises several questions. How often does this happen? Does this apply to all models, including transformers? Do CNNs and transformers use similar or different features for classification? After our first work on attribution maps, we soon realized that deep networks may not be making decisions so simplistically. There might be many different occlusions that the network would be robust to. In 2021, we proposed a search-based method called structural attention graphs. It can search for multiple part combinations that the network would predict with high confidence. One can say that different regions are revealed in these images, yet they are all classified with very high confidence. All these have led us to gain a significant amount of understandings of deep networks. However, most of these explanation algorithms explain a single image and only generate anecdotal evidence, and it's unclear how much those evidence would lead us to characterize the real differences of networks. Therefore, in this paper, our idea is to systematically evaluate explanation algorithms on thousands of images, and we hope the statistics of these explanations would help us get more insights about the general classification mechanisms of different types of networks. A main result we found out is that model behavior falls into two categories of behaviors. The first type of behavior is what we call compositional. One can see these numbers in the boxes, they refer to the likelihood ratio, denoted as the predicted class conditional probability of this occluded image divided by the predicted class conditional probability of the full image. In compositional behavior, the model builds up its confidence by jointly looking at many patches, and if you remove a few patches, the classification confidence does not change by much. We found that this type of behavior is mostly exhibited by ConvNets and Transformers trained without distilling to a CNN teacher. This significantly contrasts with the second type of behavior, which we call the disjunctive behavior. In this case, the classifier classifies with very few patches. If you look at this harvester, we only have to show their tails, and the next work is even more confident that it is a harvester than showing it the entire image. However, similar to what we have learned in SAC, there are many of these few part combinations that led to similarity highly confident predictions. We call this a disjunctive behavior because this almost looks like an OR relationship among all these conjunctions. The network only has to see one set of these evidences to be able to confidently classify an image. So in this paper, we propose two approaches. The first is sub-explanation counting. In order to introduce it, we need to first introduce the concept of minimal sufficient explanations, or MSEs. First, we divide the image into 7x7 grid and define each cell as a patch. An MSE is defined as a set of patches, so that if one only sends this set of patches as an input image to a deep network and leave all the other patches as zero or a highly blurred version of the image, the network will classify it with a high confidence compared with classifying with the entire image. Besides, if you remove any patch from it, then the likelihood ratio will be lower than the threshold. This likelihood ratio threshold is set to 90% in our experiments. There may be a lot of MSEs in each image. We follow the SAC paper and use beam search to efficiently locate all of them. Once we have MSEs, we can define sub-explanations. We construct a tree for each MSE by deleting one patch at a time from a parent node to generate child nodes. Every MSE for a given image is the root of a tree. In the meantime, we keep evaluating the confidence of current nodes. We stop the expansion if the confidence is less than 50% compared to the full image. Afterwards, we count the number of nodes that have classification confidence above several different thresholds and call them sub-explanations with that certain threshold. Comparing the MSEs and the sub-explanations across different models can help us understand the different behaviors exhibited by different models. One type of behavior is compositional, which is usually indicated by a smaller number of MSEs, but each MSE would be quite large with many patches. It also would have a significant number of sub-explanations. since removing a patch only slightly lowers the confidence. This tree is too big to be visualized efficiently, but the shell size of it shows a significant number of sub-explanations. With the disjunctive behavior instead, the network requires very few parts to obtain a high confidence prediction, but it can rely on any of multiple diverse combinations to obtain a confident prediction. Hence, there are more MSEs, but each one would be smaller. Besides, removing some parts from MSEs may significantly reduce the likelihood ratio, which leads to a small number of sub-explanations. Armed with these concepts, we are now ready to test different models on many images. These are the models we tested in our experiments. We select models with similar sizes and similar accuracy to remove a potential confounding factor of the analysis. We include older CNN models, which were trained with less data augmentation. We also have newer CNNs, which are ResNet 50 variants, trained with modern data augmentation strategies. ConvNets T and different transformers trained with and without distillation from a CNN teacher. Due to the slow speed of running all the experiments, we used the first 5,000 images from the ImageNet validation dataset in all experiments. This is the results of beam search to locate MSEs. The number on the top right are thresholds used to count sub-explanations. Most CNN, ConvNets, and distilled transformers have higher number of MSEs and smaller MSE sizes, indicating disjunctive behavior. While undistilled transformers have smaller MSE counts and larger MSE sizes, consistent with the compositional behavior. A separate result is the effect of data augmentation. Newer CNNs with better data augmentation have significantly more MSEs than older ones, showing higher robustness. One interesting aspect is the significantly higher number of sub-explanations in ConvNets and undistilled transformers. We set out to examine what is the most important factors underlying this high number. These are the block designs for ResNet, ConvNets, and Swing Transformer. ConvNets and Swing Transformer have two obvious differences with ResNet: large receptive field sizes and a different normalization layer, where they use layer normalization compared to the bench normalization used in ResNet. First, we trained ConvNets T and Swing T with a smaller kernel and window size. For ConvNets, we used 3, and for Swing, we used 4. Reducing the receptive field size decreased the number of sub-explanations by about 40%, but this did not fully explain the differences. So we replaced the original layer normalization with bench and group normalization, and further trained models with different normalizations and smaller receptive fields. Surprisingly, changing layer normalization to bench normalization very significantly reduced the number of sub-explanations by about 80%, driving ConvNets and Swing Transformer back to levels similar with CNNs. This shows that although receptive field size and normalization both played a significant role in compositionality, the choice of normalization is a much stronger factor. So, why does using bench normalization lead the network to be so much less compositional? We attempt to explain this by examining the normalization dimension of these approaches. Here we show the relations among different normalizations. Bench normalization only normalizes within a single channel and does not normalize across different channels, whereas group and layer normalization normalize across different channels. This could lead to an effect that a few large activations dominate the prediction when a network is using bench normalization. We store the average values of the maximal activation in each image for each channel in the last block for ConvNets T and Swing T variants. Indeed, the trend is clear that the top feature channels when using bench normalization are much more dominant than with group and layer normalization. recalling disjunctivism and compositionality. Last some explanations indicates disjunctive behavior, which is robust to occurrence by using a different conjunction if a key feature cannot be seen. In contrast, compositional mechanisms handle occurrence in that removing some patches only slightly lowers the classification confidence, creating a significant amount of sub-explanations. We show that notation layer significantly impacts model behavior. Batch notation leads to disjunctive behavior, while layer and group notation lead to more compositional behavior. Interestingly, distillation with a CNN teacher would lead transformers to disjunctive behavior as well, which showed that a network with layer norm is also capable of being disjunctive, but it needs a CNN teacher to tell it to do so. Having discovered the effect, the open question is whether it is good or bad. We do not have enough concrete evidence to support an outright answer, but some intuitive argument for compositionality can be made. Over-reliance on the existence of a few local features might reduce robustness to adversary example. Indeed, CNNs have usually been shown to be less robust than transformers. Another question we wanted to answer is whether different types of models use the same kind of features to classify. To evaluate the similarity between models, we developed a second methodology called cross-testing, using 1D model to generate an attribution map and then submit the masked regions as input to the second deep model. If two models rely on similar visual features, then they should score highly in cross-testing. Here is an example. We used VGG19 to generate the heat map and evaluated the masked regions using SwinT and VGG19 separately. They showed different prediction confidences. For cross-testing, we use Agos++, which is our best attribution map to date. To better visualize these similarities, we applied kernel PCA to project all models to 2 dimensions, based on insertion score similarities. This figure shows the projection results. Models of the same type use similar features for their predictions. We can roughly delineate clusters of older CNNs, newer CNNs, ConvNext variants, non-distilled and distilled transformers. And distillation brings transformers closer to CNNs. This figure shows some qualitative cross-testing results. The partially occluded images were generated using Agos++ heat maps on the networks with Boolean number. Then the same occluded image is tested on multiple networks. The leftmost example shows that if the occluded image was generated by VGG19, most transformer models have much higher confidences. In the 2 examples on the right, VGG fared quite poorly on masked images generated by other networks, showing their over-reliance on specific features that may not be present under those masks. So in conclusion, we find that different types of visual recognition models exhibit quite different behaviors along the concept axis of disjunctivism and compositionality. The choice of notation strongly affects the compositionality of the model. Receptive field size also affects compositionality to a lesser extent. With cross-testing, we found the same type of models use similar features for their class prediction. There are more results with different baseline images, different random sets, different heat map approaches, as well as more summary statistics that we do not have enough time to show here. So please check our paper for more details. And finally, we want to thank the reviewers of all versions of this paper, because this paper was rejected 4 times by previous conferences. And the reviews really led us to dig deeper and deeper, and finally found the bench nomination effect in these 5th submissions. And we also thank Dr. Tom Dietricher for his valuable suggestions, and Liang Hui Wang for assisting with HPC resources. And thanks for invitation. Okay, thank you.
Awesome. Yeah, thanks, Mingqi, for walking over the paper. I think it's very valuable work to dive deeper into the mechanism of how different backbones for vision works. Since we're running a bit low on time, maybe if the attendees have a question, you can either email him afterwards to dive into the details. But before we close, I actually do have one question. You're just kind of curious. So in this work, you mostly focus on working with image classification, right?
Yeah.
Do you think this approach can be extended into working with video? And if so, when working with video, like how do the explanation methods gonna differ?
We haven't do this at this time because before I remember some like video algorithm is not very good enough, but at this time they are good enough. Maybe we can try to extend this work to understand the video, but we haven't do this now. Maybe we can try it.
Yeah, I think I know there's like video transformer, and I think even swing transformer was being applied for video before. So I think if you extend this approach to like different video backbone, I think that'd be super cool to have a scientific understanding of how they're different, right, from traditional approach, right?
Yeah.
Anyway, looking forward. Thanks for sharing your work, and looking forward to some of the future research project coming out from Jonah. Yeah, so I think that's it for the webinar today. But once again, sorry for some technical issue at the beginning, but I think we figured it out. The recording of this webinar will be available probably within 2 to 3 weeks or so. So be sure to share with the speakers when this becomes available. And yeah, once again, thanks for showing up today, and thanks to speaker for presenting, and thanks for attendees for engaging. Really appreciate your attendance, and yeah, hope you enjoy the rest of your weekend. Bye-bye.
Bye.